Okay, determine the solubility and molar solubility of lead iodide in a 0.15 molar sodium iodide solution. Well, the sodium iodide, that's a salt. It's going to break up into sodium ions and iodide ions. And if you have 0.150 molar of the sodium iodide, it's all going to break up. That's why there's no return arrow. And we'll have that 0.15 molar sodium ion and iodide, but this is the only common ion. So we've done the common ions before. And so let's write out the expression. Got a cat here. Okay, so lead iodide breaks up into that's our solubility product equation. And when we start, we'll do the ice table. Well, nothing on this side because it's a solid. This is 0, but then we have 0.15 molar iodide, because that's what they said. We're trying to see what happens when we put this stuff into solution, into an iodide solution. So it already has some of this stuff available. And what we'll find is that the concentration is going to drop because there's Le Chatelier's principle says we're going to have to push back that way. But we're going to create some, plus x, plus 2x. We're going to create some of the product. I don't know why I'm putting parentheses around it. But we put it into our KSP expression. It's going to be x 0.15 plus 2x squared. And that's going to be equal to the KSP for this expression. Now, if we had to expand this out, we'd have a third order polynomial, which can be solved, but we don't normally deal with that. But remember our check to see if the approximation will hold, 0.15 divided by 10 to the minus 9. Yes, that's going to hold, as usual. And then we have a very simple expression. So the x is going to be equal to the concentration of the lead ion, but also the lead iodide. So we have 0.15 squared times 6.5, and we come up with 2.89 times 10 to the minus 7 molar. And just to do it real quick, if you did it without the iodide, you'd end up with 8.06 times 10 to the minus 5. So definitely the concentration dropped, as it should. Not that was just a little check, you don't have to do that. But if you got rid of this number and this was just x squared is equal to this, it would tell you the concentration of the lead iodide in pure water. And then 2.89 times 10 to the minus 7 moles per liter of the lead iodide times its molar mass will give us 1.33 times 10 to the minus 4 grams of lead iodide per liter. So these are the two that we're after. And again, we have the molar mass, we have the concentrations. If I'm off on anything, the format is correct. I double check everything, but there's just a lot going on here. Trying to get a lot of these done as quickly as possible. So, but if there's any questions or any problems, let me know. I just want to go back just real quick here. Yeah. Okay. Oh, that's the answer key. Yeah. There it is. Okay. To make sure I had everything on there. All right. Now, make sure this is on line here. Now you see that we have 0.440 molar magnesium nitrate, which is going to give us 0.440 molar magnesium ion. If you have to put this into an ice table to determine that, that's fine, but you should start getting faster at this kind of thing. If you do this problem and you set this up here, on the exam, and you put 0.440 molar, this would be 0, and you set it up like this, that'd be perfectly acceptable to me. I wouldn't have any trouble with that at all. And then, yeah, so this would be plus 3x plus 2x. Put it into the expression for this problem. So KSP would be, it'd be 0.440 plus 3x cubed. And notice I'm not writing out the full expression. I figure at this point you have to know, or you should know what's going on here. As far as just plugging it directly into here. If not, go back to the earlier videos or contact me. Okay, now the expression is going to hold, or the approximation is going to hold, so this goes. And notice if it didn't, we'd have a fifth order polynomial to solve, which can be solved, but we don't normally do those in class. Probably your calculator would be able to do it, but we try to avoid doing things that are exceptionally difficult like that. We like to make things easy. So that X is going to be the concentration of our magnesium acetate, or arsenate, I should say. It's an unusual compound. And that will be our molar solubility. I'm going to double check that. And then this is multiplied by 351 grams per mole. And this comes up to be so this is times 10 to the minus 8 grams per liter, and that's so 8.49. Okay, I want to double check one thing here. So whenever you're double checking, there's a lot of different ways of solving the problem. There are a lot of different ways of doing the algebra. What I did was I did it a completely different way than I did it previously, and came up with the same answer, so that's always a good sign. Okay.